Okay, in this section right here, it says special segments in a circle. Almost this whole entire chapter, we've been talking about arcs and angles and things like that, and different relationships between them. But this time we're going to go a little different. We're not really going to talk about the arcs and the angles. We're going to talk about the segments that these things make. So a lot of the things we've been talking about as far as tangent and secants and chords and all that kind of stuff is going to still be in here, but we're going to talk about the lengths of the segments themselves. So let's put a circle here, and let's make it a little bit bigger so we can work with it, and let's draw a couple secants. Remember what a secant is? It hits a circle in two spots. But I'm not going to go all the way through the circle. What I'm going to do is I'm going to just start and stop on a circle. So they're basically chords, but you can consider them secants as well. Let's do like this. It doesn't really matter. It doesn't have to go through the center or anything, so you don't have to be real picky on this. And this should hit. Let's make sure it hits right on the circle. There we go. That's a little better. All right, so what we're going to do is talk about the lengths of the segments. And let's label some of the segments. I could put like A, B, C, D right here, but what I'm going to do, just to make this a little easier on us, I'm going to put little a right there. And so that right there represents the length from this point on the circle to where they intersect. So that little bit right there is little a. I'll call this one B. So obviously from here down to where it hits the circle, that's B. And I'll call this C, and then I'll call this D. So I have four different segments right here. Now the first theorem that we're going to do, it's actually pretty easy. It may not be intuitive. You may look at this and say, well, okay, well, it's easy to do, but I would have never figured that out myself. And that's kind of how I would be too. But it's really easy to do. What this thing says, I'll just read it for you. It's Theorem 1015. It's on page 736. It says if two chords intersect in a circle, and that's what's going on right here. I've got two chords, and they intersect right here in a circle. They intersect inside the circle. That's a big difference, okay, from what we're going to do a little bit later on. So if they intersect inside the circle, it says the products of the lengths of the chord segments are equal. So what does it mean to be a product? A product, if you remember from your early math days, is multiplication. So I'll just put a times symbol right there. Product means multiplication. So it says the products of the segments of each chord are equal to each other. So if I take a look at this chord right here, this whole long chord, what are the two segments? A and B. The product of those segments would be A times B. We're not talking about the length of the segment, because look, obviously the lengths of the segments are not the same. This looks a lot longer than this one right here. So the lengths of the segments are not the same, but the products of the two segments, A and B, are going to equal the product of the two segments on the other chord. So that's going to equal C times D. So that's kind of interesting little thing right there, and that's a nice way to remember it. So if I multiply the two segments together, it's going to equal the product of the other two segments. You can't do this. You can't take A times C and it equals D times B. No. You take that one chord right here, and then it's split up into two segments. You multiply them together, and it's equal to the same thing on the other chord. This chord is split into two segments, multiply them together, and then those products are equal to each other. Let's do an example and see how that works. Okay, we're going to do two examples right here. This one's a little bit easier than this one, so let's do this one right here first. You got two chords intersecting inside the circle, and they're broken up into their segments. And so the product of the segments are congruent or equal to each other. So let's multiply these two segments together. I've got x and I got 10. I multiply them together, that's 10x. That should equal the product of these two segments, 5 times 12. I'll just write it out. We could just done that in our head, I guess, but I'm just going to write it out so you remember how we got that number. Of course, that's 60 divided by 10. X is 6. That's as easy as that is. Pretty simple. This one's kind of the same. But the algebra is just a tiny bit more difficult than this. So let's do this again. Let's take the product of the segments. So I'm going to take this segment right here, multiply it by this segment. So I'm going to go x times x plus 10. All right, so I multiplied those two segments together. We're going to set it equal to the product of the other two segments. So I'm going to multiply these two together. Now you got to be careful that you use parentheses correctly. Notice I used parentheses here with the x on the outside. Anytime you have a sum, anything that's being added or subtracted and you're multiplying together, you should put those in parentheses. All right, so there we go. Now, how do we multiply this through? Well, this is just straight up distributive property, so that's going to give us x squared plus 10x. Now this one, if you remember this is FOIL method, first outside, inside, last. So you can go back and look at your algebra on this, but I'll do it really quickly here. So the first is x squared, plus the outside is 8x, plus the inside, which is 1x, or just x, and then plus the last two terms, which is plus 8, because it's 1 times 8. Let's clean this up a little bit. I can add these two like terms together, 8x plus x, and let's just put it right in here just to save us a little room. 8x plus x would be 9x. And now we have to solve for x. The nice thing about this one, you don't have to worry about the quadratic because the x's actually subtract out. So if I subtract an x squared from this side, subtract an x squared from this side, they go away, which is kind of a nice thing. And now it's pretty simple. Now it's pretty basic. Subtract 9x from both sides to show that. And then 10x minus 9x is 1x. And then that cancels out. That's going to equal 8, just like that. 1x equals 8, and that is the answer. They just say solve for x, and that's all you got to do. They might possibly say, what is the length of particular chords or segments. Just make sure you look for that in case they do ask for that. On this particular question, I didn't write it down here, but it just said solve for x. All right, so that's that. Let's see what else we have on these special segments of the circle. Okay, here we have a situation where we have two things that are intersecting again, but notice where they intersect. They intersect on the outside. Those two things are called secants. We talked about that just briefly at the beginning of this lesson. It's not just a chord this time. It doesn't just start and stop on the circle. It starts on the circle and it goes all the way out here, and they intersect at a point outside of the circle. Okay, so this is a little different. We're not just going to multiply the segments together and set them equal. It's just a little bit different. So let's see what we're going to do here. Let's just change our color a little bit. Let's go blue. Okay, so what we're going to do, I'll just show you what the theorem says. This is theorem 1016 on page 738 if you want to follow along. It's a little wordy, but I think hopefully I'll make this a little bit more easy to understand. What this says is if I take this whole entire secant, right, from here. Now remember, a secant technically is a line, but we're talking about this part of the secant that just goes from this point to the circle. So we'll just call this whole thing the secant, even though technically it keeps going forever. But we're just going to say from here to here. I'll call that the whole thing, right? The whole secant. If I take the whole secant and multiply it by, they call it the external segment, or the part of the secant that's outside the circle. So if I take a look at this whole secant right here, which part is outside the circle? Well, that would be part A. It'd be segment A right here. So what it's saying is this. If I take the external segment, the outside part, which is A, and multiply it by the whole entire secant. Now, some of you guys are going to say, oh, the whole secant is AB. No, it's not AB. If I wanted to find the length from here to here, if this was 3 and this was 2, I wouldn't go 3 times 2 is 6. I would go 3 plus 2. So that's what I'm going to do right here. I'm going to go A plus B. So here's what the theorem says again. If I take the outside segment and multiply it by the whole entire secant, which is A plus B, that's going to equal the same thing on the other secant. So what am I going to do on the other secant? Take its outside part, which is C, and I'm going to multiply it by that whole entire secant. What would that whole entire secant be? It would be C plus D. And that right there is basically what the theorem is telling you. Now we'll put some numbers in here in a second. All right, but that's basically what it's saying. This is the outside segment. I'll just say, yeah, we'll just say outside segment. And this is the entire, or the whole, if you want to call it that. We'll call it secant. All right, so the outside part times the whole thing equals the outside part times the whole thing. That's how I remember it, and that's how I usually teach it. So if you take the outside segment, multiply it by the whole entire secant, that's going to equal the outside segment times this whole entire secant. And then you can solve for whatever you want to solve for. It's a little easier when you see it as an example. So let's do an example and see how this thing actually works. Okay, here's our first example, and we are going to solve for x. That's what we want. That's what they ask you to do. So what does our theorem say? It says you take the whole thing times the outside. I always like to put the outside first. Let's do that. We're going to do it. Just do it right here. Take the outside times the whole thing. Well, what's the whole thing? It is not 8x. Listen to me. This is a problem that a lot of students have. They put 8 times x. It's not. What is the length of this whole entire secant from here to here. It's not 8 times x, it's 8 plus x, or x plus 8. I always like to put the x first. So make sure you put the plus there. I can't emphasize that enough because so many students mess that up. So this whole thing is x plus 8. We're going to do the same exact thing down here. So you take the outside part, which is 6, and you multiply that by the whole entire thing. Now that's a little easier to see. And if you look at it, notice, the whole thing is not 60. It's not 10 times 6. What is it? It's 10 plus 6, which is 16. So I take the outside part, which is 6, multiply it by the whole thing, which is, I'll tell you what, I'm not even going to put 16. I'm going to put 10 plus 6, just so when you look back on your notes, you say, oh, that's how I got the 16. All right? You add the two segments together. So let's see what we get here. I've got 8x, let's distribute, plus 64 equals 6 times 16. Remember, that is 16, and if you do the multiplication, that's 96. I'll do that in one step. All right, subtract 64 from both sides. Probably shouldn't even have to do all these steps for you, but just so you see how to do everything. Divide both sides by 8. I'll skip that one. 32 divided by 8 is 4, so x is equal to 4. All right, and that's basically all you got to do with this. Okay, it's pretty simple. Again, you just have to, the math is not hard. Okay, that math was Algebra 1 stuff. It's easy stuff. But it's knowing what to do with these numbers. That's been the key to geometry ever since we've been doing it, is just knowing what to do with these numbers. Again, you take the outside times the whole thing equals the outside times the whole thing. When you do that, it's when the two secants intersect outside the circle. That's when you do it. All right, we've got one more. So we did two secants, or two chords that intersect inside the circle. We did two secants that intersect outside the circle. What did we leave out? Well, we left out a tangent. We did tangent the other day. And let's throw a tangent in here and see how that works. All right, this kind of looks like what we just did, but here's the secant, and it's broken up into two segments. But now we have a tangent. So what I'm doing is I'm looking at the tangent and the secant. Now, the reason I don't do two tangents, and I'm not going to do two tangents, because we already did it. We had another lesson that said if you had a tangent drawn from an outside point here and a tangent drawn here, those two segments are actually equal to each other. So there's no fancy math to do. You just set them equal. This is a little bit different, but this is really close to the one with two secants. Remember what we did with the two secants? You took the outside times the whole thing. Well, the tangent's kind of the same thing, except look at the tangent. It stops right here. So the outside part of this tangent is actually the whole entire tangent from the circle to the outside point. So the outside is really the same thing as the whole thing. So I would take a, which is the outside, multiply it by the whole thing, which is a, and what's a times a? A times a is a squared. So it's very similar to what we just did with the two secants, except we just took the tangent and I said, oh, the outside is the whole thing. So I multiply them together, a times a, which is a squared. And this is what we need to know when you have a tangent and a secant intersecting outside the circle. All right, let's do an example with that, and we'll be finished. Okay, in the book they give you one example, and I think the math on that is a little bit tough just to give one example. So I thought I'd do one where the math is pretty easy. Then we'll do the one that's in the actual example. This is actually one of the problems in the book. I won't tell you which one, but it's one of the ones you're going to have to do on this lesson. So let's see what we're going to do here. First of all, let's deal with the secant first, because that's got the variable in it. We're going to take the outside segment and multiply it by the whole thing. All right, so the outside is 5 times the whole thing. What is the whole entire thing? It's not 5x, it's 5 plus x, or x plus 5. Make sure that you add them together to get the whole thing, and it's the outside times the whole thing, equals, now this is the tangent. Remember, the outside to the tangent is actually the whole thing. So I'm going to go 9 times 9, which is 9 squared. So let's do some math on this. This is 5x plus 25 equals 81. Subtract 25 from both sides. And what's that? 56, I think. So 5x is 56. Divide both sides by 5. That doesn't reduce. If you just wanted to keep it, 56 divided by 5, I'd be perfectly fine with that. I have no issue with that at all. If you wanted to turn that into a mixed number, you could do that as well. But I think what the book is doing, they're just putting that into a calculator, and that would be fine too. So let's just do it the way the book is doing it, and they put 11.2. Comes out exactly 11.2, so there's no approximation, and that's what x is equal to, 11 point, put the point in there, 0.2. All right, pretty simple. Math is not real hard. Let's do another one where the math gets a little bit tricky, and we may have to be reminded of something that you learned in Algebra 1. Hopefully you learned this in Algebra 1, but we'll go through it as quickly as we can. Okay, I got to go through this quick. Bell's about to ring in about 5 minutes. So let's go through this. Let's take the outside times the whole thing equals this thing squared. I'll just put 64 down. Now watch, this is where it gets a little bit complicated. Equals 64. Now this is a quadratic. You have an x squared here, and we didn't have that earlier. That's why I said this gets a little bit complicated. I'll just show you what we do. You can look this up somewhere on how to solve quadratics. I'm just going to do it pretty quick here. So x squared plus 7x. What we're going to do is we're going to set this thing equal to 0. So that means I'm going to take the 64, put it on the left-hand side, and if I subtract 64, that's going to equal 0. This is a quadratic equation. And for quadratic equations, I can use the quadratic formula. There's a couple ways to do this, but let's just use the formula. I don't know if you remember this or not. So x equals, oops, forgot something here, negative b plus or minus the square root of b squared minus 4ac. Hopefully this looks familiar to you. I don't know if you did this in your Algebra 1 class or not, but this is what we're going to do. And we'll show you it's not so bad. Let's see. We'll put a 1 in front of here. That's the A, the 7 is the B, and the negative 64 is the C. So that's what we're doing. We're plugging 1, 7, and negative 64 into A, B, and C. Oops, there goes the bell. Kids are going to start walking in. I'll tell you what, I'm going to stop talking, and just because kids are going to be walking in here pretty soon, and I'll just write it out for you so you can see what's going on. So here we go. It's negative B. So x equals negative b, which is negative 7, plus or minus the square root, b squared, which is 7 squared, which is 49, minus 4 times a times c. And that whole thing is over 2 times a, or 2 times 1. And now it's just a matter of simplifying this. Negative 7 plus or minus square root, and let's see, that would be 49. That would be plus, I should be able to do that in my head. What's 64? Let's turn my calculator on. 64 times 4. That's 256 over 2. Negative 7 plus or minus square root. So 256 plus 49. That's 305. All right, here they come. I'm going to stop talking.